Good morning, students. Today we will start with the topic that is resolving power of optical instruments. Resolving power of optical instruments. So in the last chapter we discussed about the optical instruments, that is microscopes and telescopes. So those are the optical instruments. In that, here in this chapter we are going to study the resolving power of that optical instrument, that is resolving power of the microscope and resolving power of the telescope. So what is nothing but resolve? So first we have to know that resolve, then we move on to the resolving power. So after knowing the resolving power, then how we resolve the, that is in microscopes and in telescopes, right? So what is nothing but resolve? So resolve is nothing but make objects clearly visible, right? So that one we call as resolve. So resolve is nothing but make clearly visible. So if we observing any object, that object must be clearly visible. So that one we call as resolve. So for that, if we consider 2-point objects, so this one is one object and this one is the another object. So these two objects are close to each other, right? So these two objects are close to each other. Then when we say that these two objects are resolved means, so these objects are independently seen through our naked eyes or through optical instrument. Then we say that these two objects are resolved, right? So when we say that these two objects are resolved means these two are independently observed. That is, we can see clearly this object and this object by our naked eye or through optical instruments. Then we say that these two objects are get resolved. So these two objects are very close to each other. When we say that these two objects are resolved means these two objects are independently seen by the naked eye or through the optical instruments, right? So then we say that these two objects are resolved. So next, what is the, here one more point is that one is limit of resolution. So what is nothing but the limit of resolution? So first we know that resolve means make clearly visible. Next, resolve means if two objects are placed or close to each other, then these objects are said to be resolved means these objects can clearly visible by our naked eye or through the optical instrument. Then we say that these two objects are resolved. Next is the limit of resolution. So what is the limit of resolution? That is, the limit of resolution is nothing but these closely placed objects, that is point objects, which are at a minimum distance of separation. So if we consider, so this distance between two objects is in minimum distance. So D represents distance between A and B, that is 2-point objects separated by a distance, that is minimum distance of separation between these two objects, or angular separation, that is smallest angular separation between these two objects. So here theta represents what? Smallest angular separation. Smallest angular separation between these 2-point objects when they are just resolved. When these two objects are just resolved, then we say that that one is the limit of resolution. So if these two objects are seen from far away distance from here, if we are observing these 2-point objects, then these 2-point objects are appears to be a single object, right? So these 2 point objects will be appear single from far away distance. That is, if you consider, if you are observing from here, from this point, these two objects are appears to be a single object. So as we travel from, that is, we are approaching to here at a certain distance. From here, we notice that these are not these. The object which we are seeing from far distance is not a single object. That is, we are observing the two objects. That is, two different objects which is separated by a certain distance. So that point we call as, at this point we are going to resolve the two objects. That is, from our naked eyes we are seeing the two objects. So at this point we call as, at this point we are resolved the two objects. So from further distance we are observing only one, that is, these two are combining, we are seeing only one object. As we travel towards that object, we identify that that one is not the single object, we have two objects. When at the point we observe the two objects, so at that point we are resolving the two objects. That is, there are two objects, not the single object. So here the limit is, the distance we call as limit of resolution. From here we are identifying the two objects. So behind this point, so somewhere here means this is the minimum distance. From here we are going to resolving. After, that is, behind this point we are observing those two objects as a single object. So hence we have to know that one is the limit of resolution. So what is the limit of resolution? That is the minimum distance of separation. The minimum distance of separation, or smallest angular separation between two objects, that is 2 point objects, when they are just resolved, when they are just resolved. So this one we call as the limit of resolution. So what is limit of resolution? At somewhere we are getting resolving the two objects, that is, at a certain distance between these two objects we are identifying these are not single objects, these are the two different objects. So that point we call as the limit of resolution. That is the minimum distance of separation. Either we are recognizing this distance, that is the minimum, or smallest angular separation, or we are finding this one, angle theta. So between the two objects when they are just resolved. So this one is very important. That is the point where we are going to resolve the two different objects, then that one we call as the limit of resolution. So understand this one. So limit of resolution is the minimum distance of the separation, or the smallest angular separation between the two objects when they are just resolved. So after limit of resolution, if we move for the next one, that one is the resolving power. So here, from here we are going to start, that is resolving power. If you know the resolving power, then we can find the resolving power of the microscope and resolving power of the optical instrument. So what is resolving power? So it is the ability. So ability of the optical instrument, or it is the ability of distinguish two closely separate, that is two closely objects are not single objects, they are two different objects. That one we call as the resolving power. So resolving power is the ability to distinguish two closely lying point objects or two separate objects. So resolving power tells that these are not single object, these are two separate objects which are placed very closely. That one tells that what is that is resolving power. That is, these two are not the single object, these two are the separate objects. That one is the resolving power. So if we define means resolving power is the reciprocal of limit of resolution. So if we define the resolving power means it is the reciprocal of the limit of resolution. Here we have the limit of resolution, then resolving power nothing but it is the reciprocal. So if we write in the mathematical formula, that is resolving power, we can write that one as RP, that is resolving power, that is equals to reciprocal, that is 1 divided by limit of resolution. Right? So this is the definition of the resolving power. So resolving power is the reciprocal of the limit of resolution, or we can write it is the reciprocal of the minimum distance of separation or smallest angular separation between two objects when they are just resolved. So if we write in place of limit of resolution, we can write the definition of the limit of resolution. So here the minimum distance of separation we are going to take a d minimum, or we are going to take smallest angular means that is delta theta. Then resolving power is equals to 1 divided by either we can take d minimum or we can take 1 divided by delta theta. Right? This is the mathematical formula for resolving power. So resolving power is the reciprocal of the limit of resolution, that is RP is equals to 1 divided by d minimum. Here d minimum means the distance, minimum distance of separation between two closely placed objects, and theta is the angular separation between these two objects. Right? So this is about the resolving power. So if we move, so first optical instrument we are going to discuss is resolving power of telescope. So why we are going to use telescope means, so for telescope we are, the purpose of using the telescope is to observe the or to see the objects which are far away from us, that is for the larger distances we are observing the objects. That's why we are going to use the telescope. So first is resolving power of so telescope is used to observe the objects which are placed at the farther, that is placed at the larger distances. So in telescope we have two lenses. One lens is the objective lens and another one lens is the, this one is the eyepiece and this one is the objective. So the image is formed somewhere here. So this one is the image formed by the objective lens. So that is in between the objective and that of the eyepiece. So here the angular separation of the objects is made by the objective lens. That is the angular separation made by the objective. Right? So if we recall the diagram of the telescope, so this is the angular separation made by the object. So object is at the farther distance, those from the light rays which are coming from further distance, the object that is parallel, and it falls onto the objective, and we get the image after refracting. The refracted rays converges at the focus, and we get the image of the objects, right? So here the objective is the angular separation made, the angular separation of the objects is made by the objective, and the main use of the eyepiece here is to magnify this image, then we get the magnified image of that object. So here in these two, that is objective and that of the eyepiece, here the objects are not resolved. Objects are not resolved either by the eyepiece or by the objective. So object which we seen from the telescope, that objects are not resolved, and the main purpose of the eyepiece is to magnify the image. That is, we have to enlarge the image. That purpose we are going to use the eyepiece. So here the images also we get the unresolved images. So if here somewhere at the further distance we have two objects that is seen through from the telescope, then here also we get the two images. If here the objects are not resolved, then here also we get the two images. So for that purpose we are going to find the resolving power, right? So here, so this one is the objective lens. If the light rays which falls on the convex lens, what happens means after refracted, these rays will meet at one point, that is at the focus. So this is at the focus, the image of the object is formed. So here this lens is, that is free from aberration, free from aberration. So this convex lens is free from aberration, as the light rays falls parallelly onto the convex lens. After refracted, they will meet at the point, that is the image is formed at that point is the focus. But here what happens means the image is formed in the form of spot, that is the bright region at the middle, that is bright region in the middle, and alternate dark and bright fringes will be appear like this. This is due to the diffraction of the lens, right? So we will get like this. In the telescope the object is there. If we focus onto the object, the image is formed at the focus, that is central. The point we are getting in the ray optics which we studied is the refracted ray will meet at one point. That point is the focus, that is they are meeting at one point. But here we are not getting single point, but we are getting in the form of the dark spot, that is bright fringe, the bright region in the middle, and alternate dark and bright patterns we are getting. So this is due to the diffraction. So hence if we studied here the resolving power, then what happens here, considering the lens which is free from the aberrations, that is chromatic aberrations and spherical aberrations, that is free from chromatic and spherical aberrations, then so this one is the lens, right? So this one is the screen where we are getting the interference pattern. So this one is the diameter or aperture of the convex lens. So that one is we have taken 2a. So 2a is the diameter of the aperture. So this one acts as a slit. So this one has the circular slit. Hence we are getting the circular bright and dark pattern. So if the slit is rectangular, then we get the rectangular bright and dark pattern. So in the middle we are getting the bright region. So after that we are getting alternate dark and bright patterns. So what happens here is, so this one is the convex lens. So here the diffraction takes place. So we get the patterns like this. So at the center, that is for here. So this is the bright region from here to here. So after that we have, so this one is the bright region. Right, this is the bright region and here is the bright region. Then the radius. So here is the, this one is the circular bright fringe. So here this gives the radius of the bright region or not. So the bright region or not, that is the radius of the bright region. So if we taken here means, so from here to here, it is the angle theta. So angle theta is, here is the radius, from here to here it is or not. So this distance is, so for further objects, that is the objects is at the larger distance, the image will be formed at the focus. This one is the focal plane. So here we are getting the diffraction patterns. So as viewed from the front face, we will get the diffraction pattern in the circular region. So in the center we have the bright region, then we have alternate dark and alternate bright region. So if we find the radius of this bright region, that is central bright region, so this becomes, here is the focal length f. So here we know by the experimental, that is the radius of the bright fringe, that is central bright fringe, or bright region, central bright region is given by or not is equals to 1.22 lambda f divided by 2a, that is approximately equals to 1.22 lambda f divided by 2a. Here f is the focal length of the objective lens. So this one is the objective lens. So for this lens, f is the focal length and 2a is the diameter of the objective lens. So for this one, or we can say the aperture is 2a, or we can say 2a is the diameter of the objective lens. So here is the diameter. Diameter is equals to 2a of the objective lens. So next, here we are going to find, that is theta, the angular separation, that is minimum separation. First we are going to find the limit of resolution, then we are going to find the resolving power of the telescope. So for limit of resolution, So here R naught values becomes, that is, if we divide 1.22 divided by 2 means we get 0.61 lambda f divided by a. So if we observe here, the wavelength of the light is very less and also the focal length is also less. The aperture of the convex lens is less, then we get the R naught value is also very less. We get the R naught value in terms of micrometer or in terms of the nanometer. So, which means that this central, the radius of the central bright fringe is very smaller. So, it acts like a point object. Then, if we resolve this point object, then we can write. So, if you observe here, so here theta is the angle subtended by the bright region. Then if we write tan theta is equals to, so here what happens, that is opposite is radius or not and the adjacent side is, the distance is focal length of the objective f, that is or not divided by f. So here we are considering theta is very small, that's why we can write theta is equals to or not by f. Because theta is very small, then tan theta is almost equals to theta, right? So here we know the value of r naught, that is 0.61 lambda f divided by a. Then if we substitute here, theta is equals to 0.61 lambda f divided by a into, here we have 1 by f. So if we cancel f, then we get theta is equals to 0.61 lambda divided by 8. So this one is the limit of resolution. So this theta represents what? Limit of resolution. So we get the limit of resolution. Then by using the limit of resolution, we can define the, so here we are going to define the resolving power of the telescope. So that is resolving power of the telescope, Rp is equals to 1 divided by theta. So theta is nothing but the limit of resolution. So if we substitute theta here, then 0.61 1 divided by 0.61 lambda whole divided by 8. So the resolving power of the telescope is equals to a divided by 0.61 lambda. So this gives the resolving power of the telescope. So how we can resolve the telescope means, that is why we are going to use the telescope, nothing but for observing, for see the objects which are at the larger distance from us. For that reason, through our naked eye we can't resolve the two distinct objects, that is two objects closer to each other. So if we observe the two stars, almost we looks like that will be a one star. That's why we are going to use the telescope. From the telescope we can resolve the two stars, that is the single star is not, that is the two stars which are close to each other, then we can resolve that two stars, that is we can say that there are two distinct stars. Then we have the formula a divided by 0.61 lambda. So how we increase the resolving power? So resolving power nothing but, so if we increase the diameter of the objective lens, hence in the telescope we have the larger aperture of the objective lens compared to that of the eyepiece. So if we increase diameter of objective lens, then the resolving power will be increasing. So the resolving power is increasing, that is up arrow mark represents for increasing resolving power. So how we increase the resolving power? Nothing but, so if we increase the diameter, because RP is directly proportional to A, so if we increase the diameter of the objective lens. So this one is the objective lens. So if we increase the objective length, then automatically the resolving power of the telescope will be increases, right? So what happens if the wavelength increases? If the wavelength is increases, then the resolving power decreases. So if the wavelength of the light decreases, then the resolving power increases, because the wavelength of the light is inversely proportional to that of the resolving power. If we decrease the wavelength of light, then we get the resolving power, that is increased resolving power. So this is about the resolving power of the telescope. So in that we find the limit of resolution, and then we find the resolving power of the telescope, right? The main purpose is to distinguish the two stars which are closely separated by a distance, that is here we are considering the angular separation theta, right? So this is about the resolving power of the telescope. In a similar manner, we will discuss the resolving power of the microscope. So microscope is used to see the objects which are very nearer to us, that is for objects which are very smaller in size. So microscope is used for magnifying the images of that object, that is specimens of the cells. So resolving power of microscope. So what happens in microscope is, we have one, here also we have one objective lens, and so this one is the objective lens, that is so this one is the objective lens, and here is the principal axis. So if we place the object just behind the focal length, then image is formed somewhere here. So if we exactly place on the object in the microscope, what happens? We are placing the object on the focus. So if we place the object on the focus, then the image is formed at the infinity. For that reason, we are placing the object is just behind the focus. So here is the object. So it is placed just behind the focus, that is nearer to the focal length. Hence the distance we place the object from the objective lens is f. So somewhere here we get the image. So here also we are getting the same, that is the image is not formed at a single point, that is we are getting the bright patch, that is circular patch like this, right? So this is the image formed from the objective. So that is at the distance v, right? So here the angle separated by the lens we taken as beta here. So next the image is, here is the angle theta or delta theta, that is separated by the image to the optical center of the objective lens. So that one we call as theta. So if we write the magnification, then we can write magnification of the magnification of the objective lens is, that is equals to the image distance to that of the object distance. So that can be written as V divided by M. So magnification can be written as M. So M is equals to V divided by M. Right. So next here the aperture or the diameter of the length, that can be taken as capital D. So from here, so this distance is D by 2. Then if we write here, it becomes tan beta is equals to opposite side, that is D by 2 divided by F. So this implies here the angle is very small, hence we can write that one beta or tan beta, that is equals to D divided by 2F. So D by F can written as 2 tan beta. So here F is the focal length of the objective and D is the distance of the aperture, and the image is formed at the distance V. So we have to resolve this one. So behind, that is the result of this image. So this image, that is resolution of the limit. First we have to find the limit of resolution. So if this distance is very closer than this, then we can't resolve the object. Hence first we need to find the limit of resolution. So for that we have to write, that is theta, that is equals to, here in the last we written as R naught is approximately equals to 1.22 lambda divided by, that is lambda f divided by 2a. So here we are taken the distance as d, hence here we can write theta is equals to, so here angular separation, that is theta is equals to 1.22 lambda divided by d. So this one is the angular theta. So this theta is equals to 1.22 lambda divided by d. So we need to find the image, that is size of the image. So size of the image, that is V into theta, that is equals to V into 1.22 lambda divided by d. Right. So the size of the image, this one is the size of the image, that is we are multiplied with the V, that is distance, V into theta, then we get this distance, that is size of the image. So this is the V theta. So V theta is equals to V into, V is the distance of the image from the objective lens and theta is the angle separated by the image. So V theta is equals to V into 1.22 lambda divided by d. So now magnification, M is equals to V divided by F. So magnification we can write M is equals to V divided by F. Then if we write, then if we substitute the value for V, that is 1.22 lambda d divided by, so what happens here is, so that is first, before going to substitute here, first we need to find the limit of resolution. Limit of resolution, that is d minimum. That is d minimum is equals to v theta divided by m. So d minimum is equals to v theta divided by m. So here we know the value of v theta, then we substitute here, we get d minimum is equals to v theta. The value of v theta is v into 1.22 lambda divided by d whole divided by m. So here we have the magnification m is equals to v divided by f. Then if you substitute here, so what happens? V into 1.22 lambda whole divided by d. So this d goes to the denominator. This m value here we have v divided by f. So v divided by f. So v get cancelled. So it shifts to the numerator. Then it becomes d minimum is equals to 1.22 lambda f divided by d. So or we can substitute here d by f is equals to 2 tan beta. So here d divided by f, then we can write here only, that is it becomes d divided by f. So hence we are writing d divided by f as 2 tan beta. 2 tan beta, that is d divided by f is equals to 2 tan beta, that is from here. So this one is the result, that is limit of the resolution, that is d minimum is equals to 1.22 lambda divided by 2 tan beta. As the angle beta is very small, then tan beta is equals to, as angle beta is very small, then tan beta can be written as sin beta. Hence the limit of resolution d minimum becomes 1.22 lambda whole divided by 2 sin beta. So this one is the limit of resolution for the microscope. So next, if we place, that is if we place the refractive index between the object and, that is in this region, if we are placing the refractive index of n, that is the medium of refractive index n, then the d minimum becomes, d minimum is equals to 1.22 lambda divided by 2n sin beta. So here n represents the refractive index of the medium which is placed in between the object and the objective lens. So here n is the refractive index of the medium which is placed between object and objective lens. So if we place the refractive index, that is if we place one medium of refractive index n, then the limit of resolution becomes d minimum is equals to 1.22 lambda divided by 2n sin beta. So if we move, that is we are finding, that is we are going to find here is the resolving power of the microscope, that is RP, resolving power of the microscope, that is equals to 1 divided by the minimum, that is the limit of resolution. When we place the medium with the refractive index n, then what happens here, that is 2n sin beta whole divided by 1.22 lambda. So this one is the resolving power of the microscope. So RP represents what? Resolving power. So resolving power of the microscope can be written as 2n sin beta divided by 1.22 lambda. So here also if you observe, if we increase the wavelength, then here also the resolving power decreases. So to increase the resolving power of the microscope, what we are going to do is, we can't increase the sin beta value more than 1. So are you understanding here? The sin beta value we are not going to increasing more than 1 because it varies from 0 to 1. So the only reason for increasing the resolving power of the microscope is by increasing the refractive index of the medium. So if we increases the value of n, then the resolving power increases. So upper number represents what? Increasing. So are you understanding here? The only situation here is we have to place the refractive index n. That is, in the earlier we have the medium as air. So that air medium is replaced by another medium of refractive index n. So if this value is greater, then the resolving power of the microscope will also greater. That is, if we increase the value of n, then only we can increase the resolving power of the microscope. So this is about the resolving power of the optical instrument. So if we increase the wavelength of the light, then the resolving power of the optical instrument goes on decreases. That is, resolving power decreases. So in case of microscope, we need to increase the medium, that is in this medium, that is in between object and to the objective, we are inserting the refractive index of any medium which is greater than that of the air. Then we are going to increasing the resolving power of the microscope, right? So this one is the formula for the resolving power of the microscope. For 2 marks, they may ask what is resolving power and write the mathematical formula for the resolving power of the microscope, and what are the conditions to increasing the resolving power of the optical instruments. Then we have to write. So in case of the telescope, if we increase the aperture of the objective lens of the telescope, then the resolving power increases, and if we increase the refractive index of the medium which is placed between the object and the objective, then also the resolving power of the microscope increases in case of the microscope. So this is about the resolving power. So before going to find the resolving power, first we have to find the limit of resolution, right? So the size of this spot is less than this one, then we can't resolve this image. That is, we can't get result of the two images, right? So this is about the resolving power of optical instrument. So in the next class we are going to discuss the last topic, that is polarization. It is also the phenomenon of light. So in the next class we will discuss the polarization. Thank you.